Hello, everyone. Welcome to this webinar as part of our 2021 Analytical Extravaganza. I'm Heather Jeswa, a Senior Field Sales Engineer at Shimadzu Scientific Instruments. I'll be your moderator today, and we will hear from Jonathan Cross from Ohio Lumex, and our topic is the analysis of siloxanes in biogas using thermal desorption GCMS. Before we start, I wanted to share a couple of notes for our viewers. The webinar console has a variety of items to help enhance your experience and interaction with us. In the screen, you'll see the following items. The slides will appear on the left-hand side. Directly under the slides, you will see a resource list with clickable links relevant to the material being presented today. On the top middle is the widget for questions and answers. Please submit your questions during the presentation through this widget, and we will answer them during the question and answer session following the presentation. Just below the Q&A box are the moderator and speaker bios. You may expand the items here to learn more about us. On the right are survey questions that you may fill out anytime during or after the presentation. Finally, at the bottom pane are the icons to bring up all these widgets in case they are minimized or hidden. All right, without further ado, let's get started. Again, if you're just joining us, I'm Heather Jeswa, your moderator. Today we'll be hearing from Jonathan Cross from Ohio Lumex, and our topic is the analysis of siloxanes in biogas using thermal desorption GCMS. Jonathan Cross is the Quality Control Manager for Ohio Lumex, and he has led several R&D efforts over the course of his 8 years with the company. He is part of the core team at Ohio Lumex, responsible for developing the laboratory's analytical capabilities for siloxanes. He also sits on the ASTM D03 subcommittee, which is responsible for maintaining standard method D8230 for analysis of siloxanes in biogas. Now, I will hand it over to Jonathan.
Hello, everyone, and thank you for the introduction, Heather. Today, I want to talk to you about the analysis of siloxanes in biogas and renewable natural gas, or RNG. In order to understand why we want to analyze siloxanes, and more specifically, why we have decided to develop a siloxanes analysis method using a Shimadzu GCMS with thermal desorption, I will need to give you some background information and context. This presentation is essentially split into 3 parts. First, I will provide some background information on biogas and RNG, including how these gaseous fuels are produced and the applications for which they are used. In the second part of the presentation, I will explain how siloxanes in biogas and RNG affect the applications described in Part 1, and therefore why we want to analyze them. The established method for analyzing siloxanes in these sample matrices is ASTM D8230. Although this is a very new method, there are some shortcomings when it comes to the prescribed sampling and analytical approaches. I will give a summary of the current method and explain how thermal desorption must be added in order to meet measurement requirements for some applications. In the third part of the presentation, after having provided context for the problem, I will explain the basic milestones we have reached in developing a sorbent trap method for siloxanes using a Shimadzu GCMS with the TD30R thermal desorption system. This will include a discussion of the current status of the method, as well as how we plan to improve the method in the near future. Before we get started, I'd like to give you some background on Ohio Lumex so you can understand our experience and perspective in tackling the problem of siloxanes analysis. Ohio Lumex is a global leader in emissions measurements, which for over 20 years has primarily worked with coal-fired utilities, cement production plants, and industrial boilers. The great majority of this work has been related to sorbent trap manufacturing and measuring mercury emissions produced by these sources. Mercury was the bridge that brought our company into the gaseous fuels industry. Over the last few years, our company has diversified into multiple fields, including the development of new continuous analyzers for process control, emissions, air quality, and gaseous fuel quality applications. Our company has gained a reputation for developing methods to analyze difficult analytes in difficult sample matrices. This includes siloxanes in biogas and RNG, where there are a variety of measurement challenges. Okay, now that I've given you some background, let's get into the main content of the presentation. First, we need to start with some definitions. Many of the attendees to this webinar series may already be familiar with biogas and RNG, but I suspect there are many who are not. So let me explain what these gaseous fuels are. Biogas is a mixture of gases produced from anaerobic decomposition of organic matter. It is usually composed of 50 to 75% methane, with the great majority of the remainder being CO2. When organic matter decomposes in an anaerobic environment, methanogenic bacteria thrive. These bacteria break down the organic matter and produce methane. As I'll explain in the next slide, this gas comes from a variety of sources and can be used for a wide range of applications. For some applications, biogas must be upgraded to a higher purity to be equivalent to pipeline quality gas. This means the gas must be around 95% methane, and most of the contaminants have been reduced to be below established thresholds defined by the application's gas quality specifications. This gas does not necessarily need to be used for pipeline applications, but you will often hear RNG referred to as pipeline quality gas. Another term commonly used to describe RNG is biomethane. The important thing to understand here is that RNG is just biogas that has been upgraded by removing contaminants and the majority of the non-methane gas constituents. Now that you know what biogas and RNG are, the next question is, how are these gases produced? The sources of biogas and RNG are dairy and hog farms, wastewater treatment plants, food waste, landfills, and other organic sources. Landfills are not pictured in this diagram because this diagram is specific to biogas produced from anaerobic digesters. Biogas in landfills is not produced in a specially constructed digester, it's just produced inside the landfill mass itself, where there is very little oxygen. I will show you a separate diagram on the next slide that goes into a little more detail for landfills. The important thing to understand here is that biogas is created from a wide variety of waste products. The nature and concentration of contaminants you find in the biogas depends on the type of waste. For example, siloxanes come from the silicones present in man-made products such as shampoo, soap, cosmetics, oils, lubricants, pharmaceutical products, and a variety of other types of waste. When these products break down in a landfill or anaerobic digester, they end up in the gas stream. This causes several problems, which I will explain later in the presentation. The applications for biogas are summarized in the bottom left part of this diagram. It is important to explain a few of these so you understand why siloxanes matter. One of the most common applications for biogas is the generation of electricity. This is done by combusting the gas in specially designed internal combustion engines that are connected to electric generators. Similarly, biogas can be used as a vehicle fuel using engines that are designed to run on very low methane content fuel. Again, we're talking 50 to 75% methane. And of course, as I mentioned before, biogas can be purified to produce renewable natural gas, which has its own set of applications. Let's go into a little more detail on the purification process, using a landfill as the example feedstock. At a minimum, raw biogas coming from the landfill needs to be treated to remove most of the particulate matter and water. This must be done even if the intent is just to send the gas to a flare, which essentially just burns all the biogas without extracting any work out of it in order to convert methane to CO2. If the gas is to be used for a biogas application, moisture must be removed to a greater extent, and siloxanes should be removed. I say should, and this is important, because many biogas sources throughout the United States are not removing siloxanes, which is why they are having problems. To be fair, the type and extent of gas treatment should be based on the feedstock as well as the application. But in the case of landfill gas and wastewater treatment plants being used for gas-to-energy applications, siloxanes should be removed or they will create problems. All right, so if we look at the final stage of purification, we have biogas being upgraded to renewable natural gas. Essentially, the purification process is the removal of CO2, oxygen, nitrogen, and VOCs. This is done with pressure swing absorption and membrane systems, ideally resulting in about 95% methane with minimal contaminants. RNG has three primary applications, and all three of these are negatively affected by siloxanes. First, RNG can be used as a vehicle fuel. I mentioned earlier that biogas can also be used as a vehicle fuel, but it's important to note there are different engines rated for different methane concentrations. RNG is meant to be interchangeable with fossil natural gas, the kind we get out of the ground, whereas biogas is not. That means we should be able to compress RNG to form CNG and use that fuel in natural gas vehicles. Secondly, RNG can be used to produce electricity in the same way fossil natural gas is used, via gas turbines. Finally, and this is the application that is really gaining momentum in the United States, RNG can be injected directly into the natural gas grid and mixed with fossil natural gas. That gas is used for residential and commercial thermal applications like stoves, gas furnaces, etc. Utilities that own the pipelines are very concerned about the quality of the gas that RNG producers inject into their system, and these utilities have gas quality specifications that the RNG producers are required to meet. Gradually, we are seeing more utilities across the country adopt more detailed and strict gas quality specifications that include siloxanes. At this point, you might be asking yourself, why would we want to use RNG at all if the gas quality is so concerning? Well, the key here is that it's renewable. RNG is carbon neutral or carbon negative, depending on how you characterize it. Let me briefly explain. RNG is considered carbon neutral because it comes from organic sources that, before dying, absorbed carbon dioxide from the atmosphere during photosynthesis. Whether the waste is food, paper, cardboard, wood, or manure, the carbon in that waste originally came from a plant removing CO2 from the atmosphere. When the RNG is burned, CO2 is produced and released to the atmosphere, and the net change in atmospheric carbon is zero. Now, if you take a step further and consider how methanogenic decomposition, if left alone, releases methane rather than CO2, you can see how RNG can be considered carbon negative. Methane is a much more significant driver of climate change than CO2 because it is more effective at trapping heat in the atmosphere. Therefore, it is preferable that methane be converted to CO2. RNG creates a financial incentive for methane to be utilized as efficiently as possible, ensuring we capture and convert methane that would otherwise be unused and allowed to escape to the atmosphere. Utilization of RNG can also improve local air quality by replacing diesel or gasoline vehicles with less polluting natural gas vehicles. It is becoming more common for gasoline and diesel waste collection trucks, city buses, and other municipal vehicles to be replaced with natural gas vehicles. It's especially beneficial when cities utilize what would otherwise be a useless waste product as the fuel for those vehicles. In addition to the environmental benefits, RNG production benefits local economies in a variety of ways, including the creation of jobs. I know this seems like a big tangent from the core purpose of this presentation, which is to discuss analysis of siloxanes, but the point of bringing up the things on this slide is to emphasize the role of government in the growth of this industry. As a result of these benefits, the federal government, as well as some state governments like California, have created subsidies, credits, and other financial incentives for RNG production. Although RNG production was already increasing over the last decade, these incentives are accelerating growth in this industry. That means more RNG producers will come online, and more RNG producers will be faced with the problems that come with trying to use gas derived from waste and equipment that was designed for fossil natural gas. In the last few slides, I've described what biogas and RNG are, how they're produced, how they're used, and why production is increasing in the United States. All of that was to give you context for the siloxanes problem, which I've illustrated here. Although I described multiple ways biogas and RNG can be used, this diagram boils the problem down to the most affected applications. All four of these applications suffer from the same basic problem. When you combust gas that contains siloxanes, you get silicon dioxide. Essentially, you get sand or glass, and it forms a tiny particulate that accumulates on equipment components. This is probably a good time to talk a bit about the chemistry of siloxanes. Siloxanes are characterized by their silicon-oxygen-silicon linkage. The siloxane functional group forms the backbone of silicones, which explains why they are in so many man-made compounds. In siloxanes analysis, we focus on measuring the concentration of 9 different species: trimethylsilanol, L2, L3, L4, L5, D3, D4, D5, and D6. The species beginning with an L are linear siloxanes, and the species beginning with a D are cyclic siloxanes. Trimethylsilanol is technically a silanol, not a siloxane, but it's grouped with the rest because it contributes to silicon dioxide formation and can often be found in biogas. For engines, such as in biogas to energy or vehicle fuel applications, silicon dioxide creates a variety of mechanical issues, such as damage to pistons, cylinder heads, and valves. Periodically, these engines need to be partially disassembled, the silicon dioxide accumulation needs to be removed, and some engine parts may need to be replaced. The net effect is that the engine operator needs to spend more money maintaining the engine than they would otherwise, and in the case of gas-to-energy producers, the engine will spend more time not producing electricity. For gas turbines, the problem is similar. Over time, turbine blades will become coated with silicon dioxide, resulting in a pressure drop within the turbine, as well as corrosion and capacity reduction. Again, this results in more maintenance costs and loss of operating uptime. Finally, if we look at the gas-to-grid application, where RNG is sent to the gas grid and distributed to homes and businesses, we need to examine how siloxanes affect gas appliances and furnaces. Silicon dioxide can deposit on condenser coils and tailpipes, but the most widely discussed issue at the moment is the failure of flame sensors in residential furnaces. You may recognize that part in the top left picture if you've ever had to replace your own flame sensor. Essentially, if there are siloxanes in the natural gas being sent to your house, that flame sensor will eventually become coated with silicon dioxide until eventually it can no longer detect a flame. When that happens, the furnace will stop operating. If that starts happening to thousands of homes within an area where RNG is used, you can imagine the problems a utility might face. For that reason, some utilities, pipeline operators, and trade associations are beginning to establish gas quality specifications or tariff limits that include siloxanes concentrations. The first to do this were PG&E and SoCalGas in California, followed by others such as Dominion and the Northeast Gas Association. Essentially, the RNG producers must periodically measure their siloxanes as well as other gas constituents in order to ensure they meet the gas quality specifications required by their customer, the pipeline operator or utility. If they don't meet the requirements, they are shut in, meaning the gas supply is shut off until they clean the gas further and confirm with analysis that they have done so. Similarly, the engine manufacturers that provide engines for gas to electricity or vehicle applications have defined upper limits for siloxanes concentrations that their engines can tolerate. Some of these manufacturers have a limit of 0, which is practically impossible to achieve. For any of these applications, the biogas or RNG producer, and possibly the pipeline operator or utility, require siloxanes measurements. In order to measure siloxanes, what options are available? Well, that depends on whether you want continuous measurements or grab sample analysis. For continuous siloxanes measurements, Ohio Lumix has a GC-IMS analyzer that will measure each of the 8 siloxanes plus trimethylsilanol independently up to once per hour, then report speciated and total concentrations. This is useful for monitoring biogas and RNG siloxane scrubber integrity in order to ensure the material is replaced on time, but not replaced so frequently so as to produce an unnecessary increase in operating expense. It can also be used for other applications like pipeline gas quality monitoring. For grab sampling, and I mentioned this earlier, there's a standard ASTM method called D8230, which was published relatively recently in 2019. This method prescribes 3 different sampling approaches: Tedlar bags, Summa canisters or high-pressure cylinders, which we can group together because they're functionally similar, and sorbent traps. The analytical methods include GCMS, GCAED, and ICP-MS. For sorbent trap analysis, the prescribed method includes extraction of siloxanes using methylene chloride, also known as dichloromethane, which, as you may know, is quite toxic. I'm on the ASTM D03 committee and plan to add thermal desorption to D8230 as an alternative method to analyzing sorbent traps for siloxanes for a variety of reasons, which I'll explain in the next couple of slides. Each of the methods prescribed in D8230 has disadvantages when compared to sorbent traps with thermal desorption. The use of Tedlar bags is particularly problematic for multiple reasons. Of course, our laboratory and most other laboratories will accept Tedlar bags for analysis, but in our opinion, it's the least preferred method of collecting sample gas and shipping it to a laboratory. First, there's the issue of sample stability. Sample gas contained in a Tedlar bag will eventually be diluted by ambient air as sample gas leaks out and ambient air finds its way in. Additionally, some extremely light compounds, such as hydrogen, can exit the bag with ease, resulting in very inaccurate measurements. For these reasons, D8230 specifies a Tedlar bag sample must be analyzed within 72 hours of sampling, and some bag manufacturers even recommend 48 hours. Tedlar bags may also introduce siloxane contamination due to there being silicone-based materials in the valve stem. For example, I was once doing a project for a gas-to-energy customer and filled one of their Tedlar bags with pure nitrogen, then sent it off to their usual laboratory for analysis. The concentration of siloxanes in the nitrogen sample was similar to what was found in the customer's treated biogas, which of course made everyone skeptical of all prior measurements. Finally, Tedlar bags do not provide the best sensitivity since analysis is done with direct gas injection. Obviously, a very sensitive instrument can overcome this shortfall, but compared to concentration on a sorbent trap, direct gas injection results in far higher limits of quantitation expressed as a concentration in the source gas. Summa canisters and high-pressure cylinders provide a reasonable alternative to sampling Tedlar bags since they provide much greater sample stability. However, the cost of shipping may be a barrier for some, and this method still suffers from the same sensitivity issues as Tedlar bags. If this method is used, it is important to keep in mind the canisters or cylinders must be passivated. The sorbent trap method prescribed in D8230, once again, calls for extraction of siloxanes using methylene chloride. This is a very toxic chemical, and the extraction procedure is much more time-consuming than the thermal desorption method. Although I didn't include this point in the slide, it is also less sensitive compared to thermal desorption because only a small fraction of the extraction is injected into the analyzer, meaning only a small fraction of the total siloxanes are sent to the detector. In the case of thermal desorption, all siloxanes in the entire trap are desorbed and sent to the GCMS, so we only lose siloxanes from the GC split ratio. The next slide will cover these differences in greater detail. I mentioned earlier how some utilities and trade associations are establishing tariff limits, which include maximum allowable siloxanes. In the case of California, both SoCalGas and PG&E have established the same limits and have defined two different thresholds called a trigger limit and a lower action level, with the trigger limit being the lower of the two. Essentially, an RNG producer's required measurement frequency and freedom to inject RNG is based on whether they are below the trigger limit, between the trigger limit and the lower action level, or above the lower action level. The trigger limit is 10 micrograms of silicon per cubic meter of gas. If we use this number as a basis for determining required sensitivity, we can look at the different methods in D8230 and compare. This is really critical for explaining why we are choosing to use the Shimadzu GCMS with TD30R, so I will need to go through this table in some detail. This table compares direct gas injection, whether that's from a bag, canister, or cylinder, with sorbent traps analyzed via liquid extraction and sorbent traps analyzed via thermal desorption. In all three cases, we are using the same Shimadzu GCMS QP2020 and the same column. We have established a limit of quantitation for all 9 measured species, and if we assume all species are present in the sample, we have a total sample LOQ of 21.6 picograms expressed as siloxanes. Again, temporarily ignore the fact that trimethylsilinol is a silinol. In the end, everything is converted to a silicon basis, so that won't matter. Now, in order for us to compare sensitivities, we need to make a couple of assumptions about how the sorbent traps are sampled. First, we assume all traps will be sampled for 30 minutes. Our LE, or liquid extraction siloxanes traps, can be sampled at 0.5 liters per minute. Our thermal desorption traps must be sampled at 0.2 liters per minute due to there being a higher density of material. This yields a total sample volume of 15 liters for liquid extraction traps and 6 liters for thermal desorption traps. What we aim to do is determine the minimum siloxane mass that must be collected on each type of sorbent trap in order to reach our interlocal LOQ. Given that information, we can proceed with a comparison. First, we examine the sample dilution ratios. Direct gas injection utilizes a 1:50 split ratio, whereas liquid extraction and thermal desorption both utilize a 1:20 split ratio. However, when following the liquid extraction method, we only inject 2 microliters out of the 3 milliliter extraction, increasing the dilution factor by 1,500. What that means is the mass of siloxanes reaching the detector is only 1/30,000th of what was originally on the trap. Using the 21.6 picogram on-column LOQ and factoring in the dilution ratios for the 3 methods, we can calculate the total on-trap mass that is required for the sample to reach analytical LOQ. Accounting for volume, we can then calculate the lowest concentration that can be measured in the source gas itself given those analytical parameters, expressed as both siloxanes and silicon. Comparing the 3 values on the right to the California trigger limit, you can see that only the thermal desorption method gives us the ability to measure below the trigger limit with these sampling parameters. In reality, we could sample for a much shorter period of time and still be well below the limit. The liquid extraction method is close at 15 micrograms per cubic meter compared to the required 10, but ideally the measurement LOQ would be at least 2 to 3 times below the trigger limit, and that would require sampling the sorbent traps for much longer. So, after comparing these methods side by side, we can see that the thermal desorption method is the clear winner. This is the Shimadzu GCMS QP 2020 with TD30R thermal desorption system. You can see the thermal desorption system on the right side of the picture with the autosampler. The principle of operation is relatively straightforward. A sample sorbent trap is put in the autosampler, and when analyzed, it is put in line in the TD30R. The sample trap is heated to 300 C while nitrogen flows through it and carries siloxanes out of the sample trap and into the cold trap over the course of 10 minutes. The cold trap contains special sorbent materials that collect all the siloxanes, after which the cold trap is heated and all the siloxanes are released over a short period of time to the split valve and then into the GCMS. The advantage to this method, to reiterate what I stated previously, is that all the siloxanes from the sorbent trap are sent to the split valve, whereas with the liquid extraction method, we only retrieve a small fraction of the total siloxanes and then send that to the split valve. Now that you've gotten a basic overview of how the system works, I can break down the individual challenges we faced in developing this method. We have had the instrument for several months now, and in that time we have made significant progress in developing a thermal desorption method for traps. There were 3 primary aspects of the method that needed to be developed and optimized. First, we needed to determine the best sorbent trap material or materials. There are 9 different species that need to be captured, and they exhibit a wide range of behavior when it comes to interacting with sorbent materials. This process took a long time, but in the end, we have found a combination of 2 materials that, when used in series within a single trap, allow for total capture of all species without making it impossible to then desorb those siloxanes onto the cold trap. The first section captures heavy species, while the second section captures the remaining light species. Second, we needed to determine the best cold trap materials. We've conducted multiple experiments using a variety of cold trap materials, including Carbotrap B, Carboxyn 1000, 10XTA, and a few others. Finally, analytical parameters needed to be optimized. This was primarily related to cold trap temperature, sample trap desorption duration, the GC column itself, and split ratio. Also, I want to be clear, the method is still undergoing further optimization, so although it meets the relatively loose requirements described in D8230, we can't quite say it's finished. This diagram illustrates the basic principles for our multi-material siloxane sorbent trap. The trap is made in 1/4-inch OD glass and includes 2 sections of sorbent material separated by an inert material. The first section is a specially designed sorbent we have created in our lab and is designed to capture heavy siloxane species while letting light species pass through. The second section is activated carbon. During the course of our method development, we found that carbon alone would not work, as it was impossible to completely desorb the heavy species. By separating the species into 2 sections, we are able to recover all siloxanes. I'd like to mention a couple other basic points about sorbent traps here in case it isn't clear. Sorbent traps are sampled with gas flowing in one direction, but during desorption, the nitrogen gas is pushed through the opposite end of the trap and flows out of the trap inlet. Additionally, it is important to understand that traps are always sampled in series. That is, a single trap run includes 2 of these sorbent traps sampled in series, with 4 sections of material total. The first trap should capture all siloxanes, while the second trap is used to determine breakthrough. With our current trap design, using our in-house gas spiking apparatus, we have not observed breakthrough. And to go into a little more detail on that, this is a rough illustration of the spiking apparatus used to perform thermal desorption experiments in our lab. A liquid standard of siloxanes is placed in a quartz boat, which is then placed in a glass tube and inserted into a heated block. Sorbent traps are connected to the glass tube, and a pump with mass flow controller is used to pull the vaporized siloxanes through the sorbent trap or traps. This approach was used to test various sorbent materials. So finally, if we examine the current status of method development, we can say that it is nearly complete, as the method satisfies the requirements described in ASTM D8230. Sorbent traps can be used as calibration standards using the vapor spiking method, and these traps can then be desorbed to create a calibration curve which satisfies the correlation coefficient requirement of 0.99 prescribed by D8230. Similarly, if we compare the mass of each siloxane species recovered via thermal desorption to what we recover using liquid extraction, we measure close to 100% as expected. This is not, however, the case for trimethylsilanol. Although the performance of the method satisfies the D8230 requirements for creating a calibration curve with a correlation coefficient greater than 0.99, this is only true for 8 out of 9 species. Trimethylsilanol needs work, and we believe we are closing in on a solution right now. Regarding trap breakthrough, the sorbent trap is performing wonderfully and will likely not need to be optimized further. Spike recovery can probably be improved as we continue to optimize parameters and try other cold trap materials, although the measured spike recovery is currently well within acceptable limits. After the method is fully developed, we will update ASTM D8230 and submit the method to committee for ballot. In addition to adding thermal desorption, we will likely add more detailed calibration and analysis QC, as well as a recommendation that sorbent traps be sampled in pairs to allow for a pair agreement calculation. As we close out this research, other opportunities for method improvement will likely arise and be incorporated into D8230. Here's a list of references and reading material you may want to take a look at if you're interested in learning more. There's quite a bit beyond what I've listed here, so if you want to know more about RNG, biogas, or siloxanes, feel free to reach out to me with your questions. If you do want to ask me questions outside the allotted time we have during the webinar's Q&A period, feel free to send me an email. My contact information is provided here. I want to thank Heather Juzwa and Shimadzu for their part in this work and for giving me the opportunity to present today. I also want to thank all of you for taking the time to listen in, and I hope you learned something new.
Let's thank Jonathan for such an exciting presentation. Again, under the resource list, you can find more information about our analytical solutions. If you have not had a chance, please fill out the survey questions on the right side to provide feedback and request additional information. We encourage you and your colleagues to attend our upcoming webinars, which encompass a wide variety of application areas. The registration link is located at the bottom of this slide. This time we'll begin our question and answer session, and I have a special surprise for our viewers this afternoon. Our Energy and Petrochemical Marketing Manager, Dr. Andrew Fornadel, is going to join us and do the Q&A session with Jonathan. So I turn it over to you guys.
All right. Thank you so much, Heather, and thank you so much to our attendees, both here at the live event and those who are watching down the road on demand. A handful of questions for our presenter, and first I want to thank him again for the wonderful presentation and talk. The first question is that it was described earlier that the biogas is generated from anaerobic digestion in landfills or digesters, and the question is whether or not companies or municipalities are now constructing specific digesters to reclaim biomass.
Yes, thank you, Andrew. So that is definitely the case, especially in California. There are state subsidies for specifically dairy farms to construct anaerobic digesters and turn that into biogas or RNG with a focus on RNG. So they can get quite a bit of money reimbursed, put towards the construction cost of that digester.
Wonderful. One of the follow-up questions to that is whether or not this process of biogas or anaerobic digestion and biogas recovery is economical. Does it make money for the people doing it, or is it trending that way as R&D and workflows have improved?
Yeah, for many sources, it was prohibitively expensive in the beginning, but as there's more competition in this industry and as research is driving costs down because new products come into the market and things are getting more efficient, and then couple all of that with obviously RIN credits coming from EPA renewable fuel standards and other incentives, whether it's at the state level or federal level, it is now economical for a lot of these sources to get into biogas or RNG. There's still a pretty significant upfront cost associated with it. But, in the case of like dairy farms and hog farms, one of the ways they can get around that is essentially forming like a cooperative where multiple adjacent farms will, pitch in, work together to construct an RNG upgrading facility that's sort of centrally located, and then they can, bring all of their untreated gas to one location, treat it, and then, either put it in trucks as CNG, to create like a virtual pipeline where that CNG is carried somewhere else, or actually injected right into a pipeline. So there are ways that you can kind of mitigate those big upfront expenditures.
Sure, fantastic. One of the questions here, a couple of them, is whether or not that the sort of siloxane analysis or analysis for these siloxanes is necessary for conventional produced natural gas or pipeline natural gas, or if there are just no siloxanes present in what we would consider kind of quote-unquote normal natural gas.
Right. So siloxanes are a uniquely man-made thing. They come from degradation of silicones. You're not going to find siloxanes in fossil natural gas, geological natural gas. So it is not necessary to do siloxanes analysis for those types of sources.
Excellent. Could you please describe a little bit of the chemistry or the kinetics of the scrubbing process to remove the siloxanes? It looked like in one of the slides there was a sulfur and siloxane scrubber as part of this processing workflow. If you could describe that a little bit.
Yeah, I can give you sort of a high-level overview of it, but the specifics are difficult because it's all sort of wrapped up in proprietary trade secrets, essentially. So at a basic level, the siloxane scrubbers are going to be based on activated carbon and or silica gel, and they might come in multiple stages where you have like a rough cleanup stage and then a polishing stage. Some of these scrubbers can be regenerated, so they can be essentially heated and cleaned out in order to extend their life, beyond just a few weeks like you might get out of a basic carbon scrubber up to a year or two. But the actual, unique properties of those different sorbent materials, those different silica gel-based materials or carbon-based materials are kind of unknown because there are multiple manufacturers that produce these materials, and that's not information that they're, entirely open about.
Understood. There's a lot of proprietary intellectual property involved in these sorts of processes. An interesting question, though, about these scrubbers and filters is whether or not they could be placed in line in CNG or compressed natural gas engines in the fuel lines to absorb or adsorb these siloxanes and other materials directly, or would that be flow prohibitive?
So the question is whether these materials, as in our sorbent trap materials or scrubber materials. Sorry, I didn't catch that.
I suppose it could be either. The question's sort of open-ended. So it would be whether or not these scrubbers or these sorbent materials could be placed in line in the kind of the fuel lines of these engines to remove these components before they reach the engine.
Okay, yeah, I understand. So in the case of the scrubber materials being used right now, that is that's what's being done. Essentially, the raw biogas passes through multiple stages of scrubber materials and then goes to its end use. And like I said, those materials are carbon or silica gel based. As for whether our sorbent materials would be useful for that application, I would say that would need to be determined. I would assume probably not, because there's a difference between what we want to do with the sorbent traps and what's done with the scrubbers. So I mentioned in one of the slides that our sorbent traps, when they capture the siloxanes, we need to be able to get all of the siloxanes back off of the trap. So if we have an extremely strong sorbent that's really good at scrubbing all the siloxanes out of the gas stream, we may not be able to thermally desorb all of those siloxanes off of the trap and onto the cold trap, which is actually what we suffered from in the first couple stages of method development, where we had a tough time getting full recovery of all the siloxanes off of that trap. And so we needed to actually put another material in there upstream of the back end, the carbon-based material, that was less reactive. It wasn't as good at scrubbing the lighter species, to allow essentially those lighter species to go to the back end and keep all the heavy species at the front end. So that's sort of a unique thing about the sorbent trap, is that you're separating out heavy and light compounds in order to be able to get everything off. Whereas in a scrubber, you would not need to do that, because you never want to get the material, you never want to get the siloxanes off of the material. You just basically capture it and hold on to it forever. So it might not, this technology that we developed for the sorbent trap might not translate into that application for permanent removal of siloxanes. That's a really interesting question.
Well, thank you very much. This question just came in, and it's related to method development, which you just mentioned. Is there any consideration to using an average response factor rather than linear regression? And followed up by, are you using an internal standard in these analyses?
No. So to the second question, using an internal standard, no, we are not using an internal standard. To the first question, can we use an average response factor rather than linear regression? No, not. Yeah, so I've got my analyst here as well, and he's given me some input, and yeah, the consensus is no, we would not want to use average response factor. Okay. I also want to add something here, because we're talking about linear regression, and there's one little part of the presentation that has actually, that's a little bit outdated between that time and now, and that is, I mentioned in the very end that we had not successfully reached a correlation coefficient greater than 0.99 for MOH, or for trimethylsilanol, goes by both names. And we actually have done that now. So we have successfully reached 0.99 for all 9 species. This stuff moves fast. So it happened within the last couple of days.
That's excellent. So as you're developing these methods, this is the final question here, is what's your expected timeline to update the ASTM method for the thermal desorption sample introduction? And the second part to that question is, what's been the response within the industry? Is this something that a lot of laboratories are excited for and looking forward to?
Yeah, for sure. Okay, so the timeline. Ideally, we would have it finished by the end of the year. I think from our perspective in the lab, the method is essentially developed. It's very close to being finished, and we have a lot of content that we could put into D8230, so I don't think that part would be tricky at all. I don't think the technical details would be tricky, because we essentially have that. What's tricky really is the voting process. Sometimes that can take a really long time. You have within the ASTM committee, you have a lot of people that are voting on it and may, kick it back to me multiple times for revisions. So we'll see if it gets finished by the end of 2021. I think if we're very aggressive about it and make sure that it goes up on every ballot cycle, we can achieve that, but we'll see. And as to your second question about, whether there's a lot of excitement about this, if this is something that people are looking forward to, yeah, so when D8230 was created, the creators of the method, the writers of the method in the DO3 committee, wanted thermal desorption to be part of it. They understand that that thermal desorption is a much better method. It's more sensitive. It's going to be more efficient than liquid extraction. However, there weren't any labs that were able to provide any data. There was essentially nobody doing this, nobody with a sorbent trap and a thermal desorption method that could provide information to the committee that would be useful to incorporate into the method. and they talked about this at a conference like a year and a half or 2 years ago, one of the RNG Works conferences, where they mentioned, this is something that is needed, but there's no one out there willing to do it. And then we essentially jumped on that opportunity because we see the advantage in using thermal desorption as well, and it's been successful. So short answer to that is yes, there's a lot of excitement and anticipation, and in fact, people expect it to be done because it's really required if you want to meet these extremely low trigger levels that are present in, for example, California.
Fantastic. Well, thank you so much. This wraps up the Q&A from our end. I'll kick it back to Heather Juzwa, but I want to thank you again for the presentation and the time spent answering some questions here. So thank you very much.
Yeah, thank you, Andrew. I appreciate it.
Thank you so much, and thank you, Andy, for joining. That was a nice surprise, and we appreciate all of you for attending and participating. We'll send you an email with a link to view a recorded version of this presentation anytime. And again, we encourage you and your colleagues to attend our upcoming webinars, and the registration link is located at the bottom of this slide. Thank you, and have a great day.